Welcome to Case Study ex1, where we'll show how to apply key operators in Project Reactor's Flux class. In particular, this case study shows how to use Flux operators like just, from iterable, from array, from, do on next, map, map not null, merge with, repeat, and subscribe to create, reduce, multiply, and display big fraction objects synchronously. It also shows how to use the mono from callable operator. As usual, you can find the source code we're about to look at in the link at the bottom of this slide. We're now in my IntelliJ project for case study ex1. Let's take a look at the class ex1, which as always is the main entry point into the test program. As you can see, there are four methods under test that we're going to look at here. Test fraction multiplication sync1, test fraction multiplication sync2, and test fraction multiplication sync3 all test big fraction multiplication using a synchronous flux stream. Test map not null, as the name suggests, is a test of the Flux map not null operator, also using a synchronous flux stream. All those methods are registered with the async task barrier framework. And then once they're registered, we call the run tasks method, which will run each of those tests. Because everything runs synchronously, they just run one after another in the order in which they've been registered. And when all the computations are finished, the block call here will return with a number of tests that finished successfully, which will then be printed as the final result in this method. Let's now go ahead and take a look at Flux Ex, which is where all the action happens. We'll start by taking a look at the implementation of test fraction multiplication sync1. As always, we create ourselves a string builder or a string buffer. In this case, it's a string builder because everything's synchronous, which we'll use to log and ultimately display the intermediate results as we do the test. We then go ahead and use the Flux just factor method operator to generate a stream of big fractions. As you can see here, each big fraction has a numerator that's the value 100, and then the denominators range from 1 to 4. We next use the do on next action operator to log the contents of the computation by appending each result into the string builder, and each of the big fractions are going to be passed in as a mixed string. Next, in this chain, we use the map transforming operator to multiply each element in the stream by a constant. And you can see the constant here is the S big reduced fraction, which has a large numerator and a large denominator. What we do now is we take the results of this and we connect it up with the subscribe terminal operator. This operator, of course, initiates all the processing and will handle the results. Keep in mind that this call runs synchronously since the publisher in this case, which is the just factor method operator, is synchronous and runs in the calling thread, therefore. Of course, there are much more interesting ways of having publishers that will enable asynchrony, as we'll see later. As you can see, there are three parameters that are passed into subscribe. The first one handles the next event, which in this case will simply append each multiplied big fraction as a mixed string into the string builder. If something were to go wrong, which won't happen here, but if it were to go wrong, then in that case, we'd go ahead and append the exception name and then display the string builder after first converting it into a string. And finally, if we get a completion event, which we should in this case, we'll handle that by going ahead and converting the string builder into a string and then displaying it by using the display method in our big fraction utils helper class. The final thing we do here is we return an S void M, which is simply a static field that's defined in our big fraction utils helper class, which as you can see is just an empty mono. And that's used as an indication to the async task barrier that this particular method under test has finished successfully. We'll now take a look at test fraction multiplication sync2. As you can see here, this again starts out by creating a string builder. And this time, rather than using the just factor method operator on Flux, instead we're going to use the of factory method on list to make ourselves a list of big fractions. Each big fraction has the same value as we did for the previous test example. We do this so we can use the from iterable factor method operator to convert that list of big fractions into a big fraction stream, a Flux stream. Then we apply the do on next action operator like we had done before, except this time, rather than using a lambda expression, we're just going to call a helper method called log big fraction, which is just a bit more concise way of doing what that lambda expression had done before. As before, we call the map operator in order to be able to transform each fraction by multiplying it by our big reduced fraction. And then, as before, we use the subscribe terminal operation in order to be able to print the results out using our string builder. This is exactly the same as before, so I won't spend much more time on it, other than to note once again that all these calls are synchronous because we aren't having a publisher that's running asynchronously, and we don't have a subscriber that's running asynchronously. So everything's running synchronously. And as we did with the first method under test, we return s void m to indicate to the async task barrier that we're done. Let's now take a look at test fraction multiplication sync 3. This is actually a bit more different than the previous two methods under test. In this one, after creating ourselves a string builder, we're next going to create a random number generator, and you'll see what we use that for in just a moment. Likewise, a little different from the previous examples, this time we're going to make ourselves a built-in Java array of big fractions rather than a list of big fractions or using the Flux just factor method operator to create a stream of big fractions. And as you might expect, we're going to use the Flux from array factor method operator to convert that array of big fractions into a stream of big fractions using that factor method operator. Now, here's where things get very different. We're going to create this array and store it in a local variable called f1, which is a flux of big fractions. And then we're also going to create another local variable, which is a flux of big fractions that we call f2. And you can see here, we're going to use the flux from operator and the mono from callable operator to lazily generate a stream of random big fractions. And the reason we have to do things like this is that Flux, for some strange reason, lacks a lazy from callable factor method operator, unlike, for example, the observable class in RxJava, which does have a lazy from callable operator. So what we're doing here is we're going to generate random big fractions using the make big fraction helper method. And you can see that we create a very large numerator and a much smaller denominator randomly, and then we join those together into a big fraction using the value of method. And these are reduced because we pass in true. And then we're going to repeat the random generation, the lazy random generation, 4 times. So we're going to generate 4 random big fractions. So it's a very concise way of applying the repeat combining operator. Then what we're going to do is we're going to take f1, which is that flux which has the array of big fractions, and we're going to merge it with flux f2, which has those randomly generated big fractions using the from and repeat operators on flux. And then we're going to take the results of merging them into a single flux stream or flux sequence. And then we're going to do what we did before. We're going to use doOnNext to log them. We're going to use map to multiply them. And we're going to use subscribe to initiate all the processing and handle the results synchronously. This code is all the same as what we looked at before, so I won't spend time evaluating it again and reviewing it. And as before, we return s void m to indicate to the async task barrier that we're done with the computation. The fourth and final method we're going to review here is called test map not null. As always, we start out by creating a string builder, and then we're going to use the just factor method operator again, like we did in the first one, to generate a stream of big fractions. And now what we're going to do is we're going to use the doOnNext operator as we did before to print them. But here's where things get different from what we had before. If you recall, the previous ones we looked at were using the map operator at this point. This time, however, we're going to use map not null. And if you recall, the difference is that map not null will not emit null values. And so here's how we're going to show how this works. For each big fraction that we generate, which comes from just, we're going to see if that big fraction equals the constant 10. Here's the definition of the constant 10. You can see it's a very straightforward way to make a big fraction with the numerator 10 and the denominator of 1. And then what we're going to do is we're going to check to see if the big fraction equals the constant 10. And if it does, we're going to return null. Otherwise, we're going to return whatever the big fraction was. Well, lo and behold, this particular big fraction, the one that's occurring here second, is the one that we're going to be looking at. And you can see that that's going to be basically 10 as the denominator and 100 as the numerator. So of course, that will equal the value 10 once it's used, once it's reduced. And so as a consequence, that will return null. However, because we're using map not null, the null value will not be emitted. So we'll only end up emitting 3 values here, not 4, as we had done earlier when we were using map. As before, subscribe is the same, like we saw, so I'm not going to review it. And as before, s void m is returned as the result from this particular test method. So now that we've walked through all the code, let's go ahead and see what happens when we run it. And it's pretty straightforward. First of all, notice that all the computations occur in thread number 1, which is the main thread, because there's no asynchrony happening at all. And that's deliberate. We're just looking at the synchronous processing using Project Reactor methods and operators. Here's the results for test fraction multiplication sync 1. You can see what the results are. Essentially, these are the values we get out of here. You can see when we do test fraction multiplication sync 2, there's a bit more logging going on because we have that logging method. But the results are the same, 150, 12 and a half, 225, 450, same results, same input, same results, just different operators, different ways of doing it. For test fraction multiplication sync 3, however, there's more results because we have 8 results that are emitted. 4 are the ones that come from the array, and then the other 4 are the ones that are generated randomly using that make big fraction helper method. And you can see here the first 4, that should look familiar by now. But then after we get past the first 4, now we're into randomly generated big fractions, which, as you can see, are generating absolutely ginormous big fractions. They're huge. And so they're doing their thing. It's doing what we expect. And then finally, the last method under test, when run, will only generate 3 results. And that's because we ignored the case where the value equaled 10. So nothing was emitted in that case at all. So we end up with these results from that particular test. And it's also just a slightly different test. But the bottom line here is that when the value is 10, we emit a null, and that's ignored by map not null. So this is the end of the 4 tests that I wanted to demonstrate to illustrate some of the basic Flux operators and a little bit of mono stuff here as well. And this should give you a good sense of how to use these in very straightforward use cases to demonstrate some of the core features available with Project Reactor.